Hello and welcome to today's webinar presented by Dlubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's webinar is point-supported glass design in RFEM. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the U.S. office and also a technical support and sales engineer, and we are located in Philadelphia, Pennsylvania. My colleague Uli Lex will be your moderator, answering any questions you may have. He's a product and customer support engineer located in our Leipzig, Germany office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. I always want to encourage everyone to ask questions throughout the presentation. You can do so within this same dialog box. If by chance we don't get to all your questions, I will certainly send you a follow-up email afterwards. So regarding the content for the next hour today, I want to give a quick overview of RFEM and the add-on module concept, in particular looking at the add-on module RF-GLAS. Then we'll move into our first example, which will be a simplified approach for point-supported glass design. This will include laminated glass, and instead of modeling the details of the point fasteners, we're actually just going to represent them with nodal supports. Then we'll move on to our second example, which will be a detailed approach for point-supported glass. This also will utilize laminated glass, and we're going to go ahead and model the supporting structure in addition to this, but we're actually going to use nonlinear contact solids to represent those point fasteners. So for those of you who are not familiar with our programs, I want to explain our add-on module system. So RFEM is our main FEA program. This allows us to fully model and load a structure. We can integrate with BIM software such as AutoCAD, Tekla, Revit. We can set up all of our loads and load combinations, whether that's automatically per a specific standard or we manually set up those load combinations, and we can run a full analysis. So within this main program and the analysis, we're going to get information such as support reactions, deflections, internal forces. Now we can utilize what we call the add-on modules for design. So we have various add-on modules for steel design per the AISC or the CSA, timber, concrete, and so on. Today we're going to be utilizing RF-GLAS. So how we incorporate this with the RFEM model is in this module, we would define our individual glass layers. So that's maybe single, laminated, insulated glass. You can define those individual layers. The program will generate the global stiffness matrix automatically for us. For insulated glass, we can also define climatic loading here, so maybe temperature and altitude differences, and we can run a stress design. So this isn't based on necessarily any specific standard, but we're just going to go ahead and do a basic stress analysis of our demand stresses over our limiting design stresses to get that ratio. We also can run a serviceability design, so we can take a look at our max deflections within our main program RFEM. We can compare this to limiting deflection ratios to additionally get a serviceability ratio as well. So the type of glass structures that are possible with RFEM and RF-GLAS is, of course, single layer. And with this, we can run either a 2D calculation according to plate theory or a 3D calculation with solid elements. We can also consider laminated glass. This would consist of 2 or more glass panes with a foil or resin layer in between. Again, this is also possible with a 2D calculation according to plate theory, where we can consider shear coupling between those layers or disregard it. We also can run this according to a 3D calculation with solid elements. And lastly, we have insulated glass. This includes glass panes, a primary seal, secondary seal, a spacer, a gas, and this is only possible with a 3D calculation utilizing those solid elements, and that's because we've introduced this gas layer into our glass panel. Now, I previously did a webinar only a few months ago that really goes much more into detail on these different glass types, and in particular showing you the difference between laminated and insulated glass. For today, we're only going to be utilizing laminated glass. So I want to reference you back to that webinar on our YouTube channel if you want to take a look at some of those other glass structure types. In RF-GLAS, we have two different calculation types, either a global or a local. Now, a global is where the supports and boundary members are considered in RFEM, meaning we're going to model everything within our main program, RFEM. This will run a linear analysis only, considering 2D plate theory. Therefore, it's only available for single layer and laminated glass. Now, on the contrary, we also have a local calculation. This is where our supports and boundary members are defined directly within the add-on modules. This gets a little bit more detailed than what you'd find with a global calculation. For this, we can consider either a linear or large deformation analysis with plate theory or solid elements. So for this, it's possible to do single layer, laminated, but also the insulated glass options. Now today, we're only going to be running a global calculation. Again, the previous webinar goes much more into the difference between a global versus a local calculation. And with that, we can jump into our RFEM model. So we're going to start off today with our first example, and this is that simplified approach. So we can just give this one a name called simple, and we're going to generate our load combinations automatically according to the ASCE 7. You can see here we also have the NBC standard as well as many other international codes. Now when we check this checkbox, then those combinations will be automatically generated for us. When we uncheck this, then we can manually generate those load combinations. So we click OK, and we're immediately brought into RFEM. So you can see here we have our graphical window where we'll begin to model, and we'll see our structure generated. We have the tables to work with down at the bottom. If you prefer to work in Microsoft Excel, for example, to generate all of your nodes and lines, you can import them in here to these tables, the click of a button here. Up at the top, we have our quick tools, which we'll certainly be utilizing today. And over on the left is our project navigator. So as we begin to model our structure, all of our input data is actually going to be available in this project navigator. So we can quickly access that input data to make changes. All of our add-on modules are listed down here as well. So you can see our long list of add-on modules. This is why we have the concept pay for only the modules that you use. It keeps the software affordable, and it keeps it catered to your specific design projects that you're utilizing. So we're going to start off today with a glass panel. Now, when I zoom into this drawing grid, by default, these grid spacings are at every 1 foot, which is a little bit too big for our scale today. So down at the bottom, I can right-click on my grid and choose the option Edit. I can access my units directly within this dialog box, and immediately we'll see the option for length here. I'm going to change this to inches, increase the decimal places, and instead of every 12 inches, we're going to set the spacing at every 1 inch. I'm also going to check this option dynamically according to the size of the model. What this allows me to do is I don't have to come back in and adjust the size of my grid as my model begins to grow, but rather the program will allow the grid to somewhat grow with my model as it gets bigger. So I click OK. Now we can zoom in to a much smaller scale here, and we can begin with our glass surface. So I'm going to start off with drawing a node. Now I choose the option up here for a new node, and I can either click it in my graphical view, and you can see the coordinates are populated automatically, or I can simply type them in here. So today I'll choose a point coordinate of 42 inches, 54 inches. I click apply, and I can see that node generated out here. So to draw a new surface, you can see our drop-down box here allows for many different surface shapes. So glass doesn't necessarily have to be a complete rectangle, but realistically, it can be any one of these shapes that you see here. We even have the possibility to do curved glass. I did a webinar maybe a couple years ago on curved glass as well, so that's always an option. For today, we will stick with just a typical rectangular glass panel. So the first thing I need to define is the material and the thickness. And the default here is concrete. It actually does not matter at this point in time what the material or the thickness is set to. This is purely a placeholder. We're actually going to override that within the RF-GLAS add-on module later on. So the fact that it's concrete, the fact that it's 8 inches right now, that's okay. We're really just setting up the geometry here, and we'll override the materials later. So I snap from the origin out to that node that I just created, and you can see here we have a typical 2D surface element. The next thing to do is to define where we want these point supports on this panel. So we're going to assume that this is a canopy type structure and it's going to be supported at 4 different locations. So I'm going to add in a new node here. And again, I'm just going to type in the coordinates. My first coordinate is going to be 33, 10, 0. I click apply. My second coordinate is going to be 10, 10, and 0. I click apply. So if I turn this into wireframe view, you can see those nodes that I just generated here. If I hold down my control key and select both of those nodes, I actually want to copy these over to the identical other side of this panel. Well, we could use the move copy tool, but we also have what's called the mirror function. And the mirror function's exactly as it sounds, probably similar to what you've seen in AutoCAD. And you'll hear me say this quite often, but a lot of AutoCAD-like features integrated directly within the program RFEM just to make our lives a little bit easier. So sometimes it's better to even forego a DXF import because it's just as easy to draw the structure within RFEM itself. So what we can do here is to create a copy, and we're going to mirror about the global ZX coordinates. Then we just select a point here that we'd like to mirror it about. Well, again, similar to AutoCAD, the program has these snap features already in place, and you can control those snap settings down here. And they include things like quarter points, midpoints, parallel, perpendicular. So you can see the program automatically detects the midpoint of this line. So we can select it, we click OK, and automatically we have our additional 2 support points on this glass panel. So now that we've defined the basic geometry here, what we'd like to do is use linear springs to represent the point fitting system. Now, we're going to do this with a new nodal support here. And when we choose a new nodal support, we can select a new type. And this is where we're going to be putting in our spring constants. And these spring constants should really come from a technical approver from the manufacturer of the connection system. So again, this comes directly from the manufacturer. Now, with the simplified approach, I'll reference the DIN standard, which is the German standard, a few times. And that's because this standard is pretty clear about this simplified approach. And I didn't really find anything too similar with ASTM regulations here, but the DIN standard gives upper and lower limits for this spring approximation. So you can also reference that, but most likely we get it from the manufacturer. You also may want to account for the additional stiffness from the substructure. So perhaps we have members holding up this glass panel. Well, you want to include that with the spring constants here as well. So for our manufacturer, we're going to release the moment. And for our translation supports, I'm going to type in here, again, information I got directly from the manufacturer of 23.57 kips per feet in the X and Y directions. Those are the lateral directions. In the vertical direction, we have something a little bit higher at 137.04 kips per feet. And I click OK. So all I need to do here is just to highlight over my node supports that I've created. So once we are complete with this and we take a look at our rendered view here, we have an issue. And that issue is what will happen when we run an analysis eventually after we load it and everything is we're going to get what's called a singularity. And singularities occur at situations like this where we have our nodal support framing into this teeny tiny little Efi Mesh point here. There's absolutely no load distribution. So the problem is that this leads to high stresses, high internal forces, and eventually we have an over design of the glass panel here. So somehow we have to separate out these singularities in order to design the larger panel here. Well, through numerous studies, which I'll reference a book a little bit later on along with the German standard, it's been found that how we want to separate out these singularity locations is with what's called a local area. Now, this local area, the radius is equal to 3 times the borehole diameter. And the borehole diameter comes directly from the point fastener that we might be using. So what we have found through these numerous studies is that whether the borehole is modeled at this point support fixture or not, it has absolutely no influence on the larger global design here of our panel. That's as long as we isolate out that local area. So how do we do this? Well, we want to add in an opening into our surface, and you can see my openings are available in my toolbar up here. Again, many different shapes, but for this one, we will choose a circular opening. So what I can do is to select a nodal support here, and then I can just simply either snap to a point on my drawing grid, or I can give it a radius. Now again, I'm assuming that my borehole diameter here is 1 inch. Therefore, my radius is going to be 3 times that at 3 inches. And there's my first opening. So what I can do is just take this opening, hold down my control key, and copy and paste it to every additional support setting here. So this is called the drag and drop feature, extremely useful for just making a quick copy, again, holding down the control key and drag and dropping. So now we have these what we call local areas defined, separate from our global panel here. But the problem is now we have absolutely nothing supporting the global panel. So we do need to go back in and define separate surfaces here to connect it back to the global panel. We can do this by selecting the boundary lines for our surface. Again, concrete doesn't matter, 8 inches doesn't matter. It's purely a placeholder, and we'll override that in just a minute. So now I just simply select these circular elements for our opening, and now we have these additional local surfaces defined. Okay, so moving on now to the loading. We can come up here to our toolbar and apply a new load case. The first load case is going to be dead load, and the action category is set according to the ASCE 7. We'll select dead load here. Self-weight is automatically included with this particular load case. For our second load case, we will call this one snow with the action category of snow. Self-weight is unchecked because we don't want to account for it twice. So that's the simple loading we'll be doing for our example today. We jump to combination expressions. The program is letting me know, okay, I'm going to generate both LRFD and my ASD combinations from the standard. Now, most importantly, the load combinations tab is going to show me those individual load combinations listed out. So we have 2 for LRFD and 2 for ASD. Fairly simple. It's only based on the load cases that we defined under that first tab. So now we have set up our load cases and combinations, and we can select them here from our drop-down. Now, as for dead load, we're just going to keep this as self-weight only, so I'm not going to apply any additional loads here. For snow load, as you can see, I've now selected it here in my drop-down. We want to apply a new surface load. This surface load is going to be applied in the global Z projected area. Now, what projected means is that if our surface here was at an angle, the program would automatically account for that angle and adjust the magnitude as necessary for a projected load. Now, for this first example today, it doesn't make much sense. We just have a flat surface, but in our second example, it will be a little bit more clear. The magnitude is going to be set at 0.03 kips per square feet in the vertical Z direction. I can zoom out, and I'm going to select all of my surfaces, including those smaller local surfaces. So now we can scroll through to our load combinations here to see both dead load, which is only self-weight, so we won't see that visually, and also snow load with the applicable load combination or load factors here. So a couple more things to do before we're ready to run the analysis. The first is the Fe Mesh. So I'm going to turn off my grid here, my drawing grid. And under Calculate Efi Mesh Settings, the default mesh is set at 1 foot. Well, this is entirely too big for our model today, so we'd like to set that to something smaller like 1 inch. And we can regenerate that Efi Mesh when we click OK. Let me turn this to wireframe view. And now you can see the Efi Mesh is automatically calculated here. It's connected to nodes, to lines, to our nodal supports. Everything is done automatically based on that global setting. But what I'd like to do is to select these center nodes here for my point supports, and I'm holding down my control key to select all 4 of them. I can right click and I'm going to add an Efi Mesh Refinement. So we create a new Efi Mesh Refinement here. The program detects, okay, it's obviously about a node. We give it a radius and we'll leave this at 5 inches. The target inner Fe length might be something like 0.1 inches and the outer length might be something like 0.5. So we're going to create a smaller mesh for these surfaces. So I click OK. We can go to Calculate, Generate Fe Mesh if we're just curious to see it. And now you can see we have a much smaller Fe Mesh which transitions back into our global settings. So Fe Mesh is incredibly important. You want to make sure, especially for elements this small, that we have enough Fe Mesh points here to get an accurate analysis. Now, in a similar fashion, if I turn this back to rendered view and I hold down my 4 local surfaces here to select all of them, I can right click to edit this surface and we have what's called a grid tab. Now a grid tab is different than what we see with Fe Mesh points. So our results are presented to us in one of 2 ways for surfaces. Either by the Fe Mesh points in some places and in other result areas it's represented by these grid settings. Now what's nice about a grid is that it's going to be in a very nice orderly fashion, whereas Fe Mesh points might be kind of every which way. It just really depends on how the program determines how this Fe Mesh should fit together. So that's the purpose of these grid settings. Now for these smaller surfaces, we want to change it to polar here, and we need to give it a smaller grid distance than 1 foot. They're small. So therefore, if we choose every 0.1 inch, then we're going to see our results at the spacing defined here. If we don't do this, we end up getting an error later on in the glass module saying, wait a second, I'm trying to present the results to you at the grid points, but there are no grid points on these surfaces. And that's because you need to go back and refine that. Maybe the same thing for our global panel here. We can just double click it and maybe we set the grid spacings here to every 1 inch. Okay, so we've loaded it, we've defined all the geometry, and we realize that we still have concrete defined for all of these surfaces. So this is where I want to make the clear distinction that we want to launch the add-on module RF-GLAS. So I locate it here in my project navigator, I double click it, and as I mentioned, the add-on modules pops up within the main program, nothing more than just a simple dialog box. So all of my information back in RFEM is going to be utilized in addition to our add-on module here. Now, as I mentioned within the PowerPoint, we are going to run a global calculation. This is really going to simplify a lot of things within RF-GLAS. And again, I want to refer you back to the previous webinar to see the major differences between a local versus a global. The standard is set to none. Now we do have the German standard here, but by utilizing the none, we're just going to run a basic stress analysis and design. The surfaces that we want to design, we actually are only interested in designing our global panel here. I'll let you know in just a minute the steps that need to be taken to design these local surfaces. But for RF-GLAS and by means of this simplified approach, we only want to design the larger panel. The ultimate limit state, we want to choose our factored load combinations here, depending on if you're doing ASD versus LRFD design, you can choose your load combinations accordingly. For my serviceability, I will choose my unfactored load combinations here. Then it's really just as easy as moving down this list. So I move on to layers. This is where we define those individual glass layers for either laminated glass, insulated glass, or even single layer. So the first thing we want to do is define all the surfaces here that this material should apply to. And this is where I can graphically select all of my surfaces. Although we're only designing our larger panel here, I still need to define the correct material for my smaller surfaces as well. We can't leave those as concrete. Then we define our first layer type, and that's going to be glass. Now we can access our material database here, and what would typically populate when you first launch this material dialog box is usually just a bunch of German glass materials. Now, likely you're going to get this information from the particular glass manufacturer that you're using. So what you can do is just to add a new material to your database. And once you add a material to your database once, it will always be in that database for any additional RFM models. So you can see here that I've added thermally toughened float glass, ASTM, to my particular filters over here on the left. So now I can always access that material for any additional models. So you can see that listed here with the applicable material properties. And I click OK. The thickness will be set to 0.31 inches. My second layer for laminated glass is going to be foil. So again, this is some type of foil resin layer in between our two glass layers for laminated glass. We access our material database here, and what would typically populate are quite a few different options here. You can see we do have some ASTM materials, some different manufacturers, as well as code independent. So again, if you don't see your particular material here from your manufacturer, just go ahead and create a new material with this button down here. So today we'll just be utilizing PVB 22 degrees Celsius with the applicable material properties shown, and I click OK. Then I give this a thickness of 0.06 inches. And finally, my last layer of glass will be that thermally toughened float glass, and the program populates the same thickness, 0.31 inches. So what's happening behind the scene here is that each individual layer has its own stiffness matrix. We can view that with this button here. And what the program is doing is the applicable calculations to create a global stiffness matrix for this laminated panel. And you can view those entries here. It's going to export this global stiffness matrix back out to RFEM to run the calculation with the correct material. So that's why I said we're no longer going to be utilizing concrete. It was just a placeholder until we could get to RF-GLAS to define these individual layers. One other thing I'd like to do under the details here is to turn off the coupling between the layers for my laminated glass. I go into much more detail on these particular settings in the last webinar as well. And finally, we have serviceability data. Well, here is where I can graphically select the surfaces I'm interested in deflection, which would obviously only be this global surface here. And the reference length would be set as the minimum boundary line, the maximum boundary line, or user defined. So we'll use the maximum boundary line here, L equals 4.5 feet. Now the question is, well, what is the limiting deflection ratio? And that's set under the standard. So for our example today, we're only utilizing this top line, which most likely you will. The other types of combinations are more geared towards the Eurocode. So for characteristics, the default for simply supported is L over 100 and L over 50 for cantilevers. So you can always override this information to however you see fit. Maybe this information comes from a manufacturer. For today, we'll just use this default L over 100. And just like that, we're now ready to run our calculation. So you can see it solves within a split second. We're just exporting out that global stiffness matrix back out to RFEM, applying the snow load and dead load, and eventually we're presented with our results in RF-GLAS. So I'm going to jump to the max stress ratio by surface. Now remember, I'm only designing this global surface here. So what we're going to be presented with are tension stresses. So we can see those tension stresses, and it's a little bit difficult to see. There is a red arrow here, but because we're looking at a rendered view, it's a little bit difficult to see, but the program is synced up in the background with the table here. We can also view our shear stresses. We compare these tension stresses with the limiting design stresses based on the material only, and eventually we get a design ratio. So relatively low here, 0.17. We also can take a look at the max displacements. Again, this is just going to take a look at the deflections within RFEM after it ran that calculation with the correct stiffness matrix, compare it to that L over 100 that we set, which is 0.54 inches, and I get a deflection ratio as well. So all of this information, by the way, can be exported to Microsoft Excel. This might be a little bit more useful if we have multiple glass panels, we want to do further design with it, or whatever your needs are. We can also view this information graphically. So what I mean by this is that we're back in RFEM, but we're technically still within this add-on module RF-GLAS, and we can see that from our drop-down box here. So we have our different load combinations, our LRFD and our ASD, and we can actually select layer number 1 or layer number 3, the top, the middle, or the bottom. From there, we can view our stresses, including our tension stresses and our shear stresses, and how those vary for the different load combinations. So this is purely for this global panel. Now we might be thinking, okay, well, obviously these local surfaces are a pretty important design aspect of point-supported glass. So how do we design those? Well, for this, I'm going to jump back to the PowerPoint here. Now, as I've already mentioned, I'm referring to the DIN standard, the German standard for this simplified application here for point-supported glass. But I also found a really helpful book called Challenging Glass with a few different editors listed here that gives much more insight to this simplified method. And what these references tell us is that, of course, we first have to design this global area. And we actually just saw that with RF-GLAS. We're going to take the max tensile stress, which is sigma 1, 2, xy, and we're going to compare it to the limiting design stress. Well, in our case, we just did that with RF-GLAS. We saw a design ratio of about 0.17. We also want to check the deflection. Again, this is what we just saw with RF-GLAS. We take our max deflections from running the RFEM analysis, we compare that to our limiting deflection, L over 100 in our case, and we're going to get a deflection ratio. Now, as far as the local area, this is actually a linear superposition of various stress components, and those stress components are listed here. Now, these are calculated individually based on maybe our support reactions from our spring supports, as well as a little bit other information. So again, you want to reference back here to these standards and references in order to get more information on design of these local areas, which we just simply don't have time for today. And eventually we're going to compare this to the design stress from whatever technical regulation that we're using in order to get the design ratio of those local areas as well. So that is a quick approach here for a simplified method. Now we want to move on to a more detailed method. So for this, we're going to jump back to RFEM, and what I'm going to do is to create a new model here. And this new file is just going to be called hardware. Perhaps what I suggest doing is modeling these different point fasteners as almost a template model. And what we can do is have several template models depending on what type of point fastener we're using or whatever type of connection. And what you can do is eventually just copy and paste these into various RFEM models. So perhaps we have a different glass panel for a different project. Well, by saving these templates, it saves us a ton of time rather than modeling all of these contact solids and everything every single time. So what we're doing right now is just creating a template. I'm not going to run an analysis. I'm just purely setting up the geometry. So therefore, I don't really care about load combination generation. We'll set up this first model here. And we're going to zoom in. Again, the grid settings are spaced a little bit too far apart at 1 foot. So we're going to adjust this here back 2 inches. And this time I want to set it at 0.5 inches. We're on an even smaller scale. Again, I want this to change dynamically with my model. We can zoom in here and you can see we have many more points available to us. So we start off with drawing a basic panel here to represent our glass. So we'll utilize a rectangular surface. Concrete, doesn't matter. We're going to override that. If you want, you can set the appropriate thickness just for this template file here. So I snap from my origin, and I'm going to snap down here to any arbitrary point. It doesn't really matter. And we're going to zoom in to a particular point where we want to begin modeling this point fastener. And I'm going to apply a new opening. Now this opening is going to represent here my connector disc. So this is the total diameter of the entire hardware at this point support. So I think it's a little bit easier here to turn this to wireframe. I snap to the point where my support will be located. And again, this is just arbitrary because we're just setting up geometry. And I give it a radius here of 1 inch. So I know my connector disc has a total diameter of 2 inches. Therefore, this is what I'm modeling here. Now, we've modeled this opening for our entire point support, but what we also need to model is a smaller opening for our bolt to pass through. Well, we can do this by drawing here a new line element. Now, a line element is exactly as it sounds. It's not a member. It's purely a line like what you would see in AutoCAD. Line elements define the boundaries of supports, surfaces, for example. So we can start off with just a basic straight line element. I'm going to snap to a point here at 0.5 inches to my outer circle. And I'm going to do the same thing on the other side. Then I'm going to utilize this line element, which is an arc via 3 nodes. So now what I can do is to click on 3 different nodes here, and the program will automatically generate my arc with a radius of 0.5 inches. And I do the same thing on the other side. So this is going to represent that hole where that bolt or rod or whatever type of support is passing through this glass panel. Turning this into a rendered view, we can maybe visually see that a little bit better. I want to use this option here to connect lines or members. So when I choose this tool, I'm going to highlight over this outer node on the left side here as well as our right side. And maybe going back into wireframe view, what I had just done is split this outer circle into 2 separate line elements. We're eventually going to create a contact solid on the left-hand side here as basically a half donut shape and a contact solid on the right. Now, a requirement within RFEM for a contact solid is that it's defined by 4 boundary lines. So this I really can't stress enough because it's really a drag when you get done with all of your modeling and you load it and you go to run a calculation, the program throws up an error and says, wait a second, something's wrong with your contact solid. So it has to be defined by a total of 4 boundary lines. So that's why I pay careful attention here to make sure I have 1, 2, 3, 4. 4 boundary lines total to define my contact solid. Not 5, not 6, not 3, but 4. So what I can do here is draw a new surface element by selecting the boundary lines. And again, concrete, doesn't matter, it's a placeholder. We click these 4 different lines here that begin our contact solid, and I turn this back into a rendered view. And to create a contact solid, what we can do is to right-click on this surface and extrude it into a solid. Now, before I get into the details of the height and even more so, let's jump back to the PowerPoint. So what I want to do with this PowerPoint is to explain here a little bit of the hardware modeling geometry. I think this is incredibly important and can be a little bit confusing when we go to model within RFEM. So what I've done is I've taken a hardware fitting from the Glassline GmbH company. So this is a German company that provides connection supports for point supported glass design, and they have provided this picture here. So this is a cross section. So we have our glass panel on the left and right hand side here. As I mentioned, we've already created that hole for our steel bolt or rod to pass through. Now at the top and bottom of this hardware fitting, we have some type of steel surface most likely. We're actually going to represent that in RFEM eventually with rigid surfaces. We don't really care much about designing these steel surfaces, so that's why we represent them with just a solid rigid surface. What we are going to model though with the contact solid is this fitting. Now this fitting represents some type of fiber gasket, a plastic washer, maybe a silicone washer, a rubber seal, or whatever type of material that comes from the manufacturer. So you can see here that we're going to essentially model 4 contact solids for 1 point support, 2 at the top and 2 at the bottom. So these are those half donut shaped that I just showed you that we begin to model. We have 2 on the top on the left and right and 2 on the bottom on the left and right, because we obviously don't want this steel sitting right on top of our glass panel. So that's the purpose of this fitting, which eventually represents the contact solid within RFEM. Again, 4 boundary lines for each contact solid. So just really keep that in mind when we're modeling these complex elements within RFEM. The contact solid depth is equal to the fitting thickness. So what I mean by that is our top contact solids are going to be 0.118 inches. That's just information that comes directly from the manufacturer. On the bottom, we're going to have a little bit thicker here for our fittings at 0.157. Now, when we eventually define our contact solid, the program requires us to define a top and bottom surface, surface A and surface B, to sandwich this fitting material here. So our surface A is actually going to be that rigid surface that represents our steel. Surface B is going to be this glass surface. So for this contact solid in particular here, rigid surface on top, glass surface on the bottom, and it will be vice versa for our bottom contact solids. The solid material is just simply set to the fitting material and applicable stiffness. Again, probably coming from the manufacturer, whether that's rubber, plastic, silicone, whatever material. And eventually we want to define nonlinear contact properties. So for this contact solid, the whole point is that we want it to fail under tension, meaning that if the steel surface here and the glass surface are in tension, we don't want any force transfer between these elements. But on the contrary, if we have compression between these elements, we certainly want the transfer of forces through the steel, through the plastic, down into our glass surface and beyond. So that's what we'll define here with a nonlinear contact solid. Now, as far as the contact parallel to the surface, this refers to the shear stresses. We basically will set this if the failure exists for contact perpendicular surfaces, then it will also exist for parallel. But in the event we have compression, then we'll see full force transfer and stress transfer for both normal stresses as well as shear stresses. So that's a little bit more information on the geometry that we are going to model here within RFEM. So we want to give it a height here, and as we just saw within the PowerPoint, this height is going to be 0.118 inches. Now it's negative because we're basing it on the local axes of the surface, which are facing downward. So what we can do here is click Apply, and now we have our 3D solid element, which we can view. So I'm going to double click on this solid element, and the solid type is going to be changed to contact. The material here, as I just mentioned from the PowerPoint, we're going to access our material database, and for my example today, I've added in here glass-lined GmbH fitting. So you can always add in that material if you don't see it here for rubber, plastic, silicone, or whatever material comes from the manufacturer. Give it a name. Make sure you put in the applicable materials for the stiffness. We add it to our database. We'll always have that option available to us for any future models. So for today, I'm going to use this material that I applied here that I've added to my material database for the stiffness of this contact solid. Under the Contact tab, we want to first select our top surface here, which will eventually be a rigid surface, and the program automatically detects the bottom surface as surface B. The contact perpendicular to the surface is going to be set as failure under tension, what we just covered. The contact parallel to surfaces, it's going to fail if the perpendicular to surfaces also fails. So that's that nonlinear behavior, and we click OK. We need to set the materials for our top and bottom surfaces, surface A and surface B. The program automatically defines all boundary surfaces that define a solid element as null. So what we want to do here is double click on our top surface and instead change the top surface stiffness to rigid. That represents that seal connector disc. Then we can take a look at the bottom of our contact solid here, and we'll select our bottom surface here. We can double click on it. We're just going to change this to standard with the concrete material for now. Again, we'll override it later, not a big deal. So we've defined our first contact solid, but we need to create an additional contact solid on the left side here. So an easy way to do that is to turn this into wireframe view. We can select all of our elements on the right-hand side, use our mirror tool. We create a copy about the global ZX plane, and we can easily just select a point here in the middle, and we click OK. We've automatically generated that contact solid on the left side here. So for the bottom side, we also need two contact solids. So again, what I'm going to do is turn this into wireframe. It's just a little bit easier to work with. Highlight everything. Use my mirror tool once again. I'm going to mirror about the global XY plane in this particular case. Same point, creating a copy. I click OK. And just like that, if we turn this into a rendered view, maybe we turn off our grid and we take a look at the elevation view, we can see here that we have 4 contact solids, 2 on the top, 2 on the bottom. Now, remember I said that our contact solids on the bottom, though, are a little bit thicker. So what we can do is just to highlight all elements on the bottom here, selecting from left to right, and we use our Move Copy tool. So for this, we just want to move these elements down an elevation of 0.039 inches, and we click OK. So now we have a little bit thicker rubber seal, for example, at the bottom. Okay, so the next thing to do is to create our bolt element passing through here. So what I want to do is to first draw a new node, and I'll just select that center element, center point on my drawing grid here. I take that node, I right click, and I'm going to move it. I'm going to create one copy in the vertical direction, 0.118. That lines up with the top of my rigid surface up here. I do the same thing with that center node to move copy it, and this time to an elevation of negative 0.157. That lines up with the bottom of the rigid surfaces. So in order to draw a bolt element, all I need to do is go to draw a new single member. The bolt element is going to be defined as a member type beam. It can take tension, it can take compression, and we create a new cross section here. So up pops our cross section library, and we can easily just select a round bar. With the round bar, I give it the diameter 0.75 inches. Now my material is also set for this bolt element. So I can access my material database, and you can see here we have many different ASTM materials. As you can see, the list is fairly large. If by chance you don't see your material that you would like here, you can always add your own. For example, I added steel A325. For today, maybe we just use steel A36. Again, this information should come from the manufacturer, so if you're not using these materials listed here, just add your own. I click OK, and just like that, I snap from the bottom node up to the top node to create my bolt element. But if I turn this to wireframe view, you'll notice this bolt is currently not framing to any part of the point fastener here. So what we need to do is to add an additional rigid surface at the top of this bolt to make sure it frames back into the rigid surfaces here of our fitting. So for this, we will draw a new surface element by selecting our boundary lines, and the stiffness will be set to rigid. All I need to do here is to select my exterior boundary lines, and the program will automatically generate that rigid surface. I do the same thing at the bottom of my bolt, and I can right click to exit this, turn this into the rendered view, and now you can see we have an additional rigid surface at the top and at the bottom here to define the force transfer from the bolt back to the surfaces. So this bolt is going to take over those tension forces when this contact solid fails. Okay, so a few other things to do. Number one, we want to take care of our Fe Mesh. It's good here to go to calculate Fe Mesh settings. Let's just change our global Fe Mesh to 1 inch again. This is exactly like what we saw previously. I do want to add in an Efi Mesh Refinement here. So I can right click on my center node, add an Efi Mesh Refinement, just like what we saw previously, a radius of 5 inches. The target inner Fe length, though, is something much, much smaller. We're working with very small elements here. So our outer length might be something like 0.2. So we're going to transition from 0.004 to 0.2 back to that global mesh setting of 1 inch, and I click OK. So now we can see the global Efi Mesh Refinement symbol here. Now, keep in mind with the smaller surfaces here, as we saw previously, we want to edit these surfaces. And under the grid, we want to change the polar settings here to something like 0.1 inches for those smaller surfaces. That's important later on. So what we can do just to show you, remember, this is just a template model. Going to calculate, generate Fe Mesh. And the program is now generating quite a bit more Fe Mesh elements, but I can turn off my grid, zoom in here to see all of the Fe Mesh elements for all of my surfaces here. Again, it transitions back to that global Fe Mesh setting for my overall panel. So this is the hardware setting that we want to save, and we can insert this in now into other models based on maybe whatever type of manufacturer we're using. So what we can do is to highlight both, actually, let me try again. I'm going to highlight from left to right here to highlight only my support as well as the Efi Mesh Refinement. Notice I didn't highlight the global panel here. And I only just need to hit Control-C on my keyboard to copy it. We jump back to this simple model that we were working with previously. So this should look familiar, and what we're going to do now is we're going to turn this into a more detailed model. So we turn this to wireframe view, and what I can do is to highlight by holding down my control key all of these elements here. And actually, let me try that again. I didn't select everything. So we highlight all of these elements holding down our control key, and all we need to do is to go back over these center nodes here. I want to continue holding down my control key to keep those center nodes in my model. So I unselect them, I hit delete, and now we can see that other than this single point support, which we can delete that as well, we're left with our original panel with the 4 support locations. So now I want to insert in those detailed contact solids into this panel. So all I need to do is hit Control-V to paste these in. Now, my offset is defined here by each model's origin. So you can specify an offset here, or once it's imported in, you can simply use the Move Copy tool. So lucky for us, it lands on exactly the point support that we want it to for this glass panel. Well, I've only inserted one here from my template model. I can use my Move Copy tool to create one copy, and I'm going to zoom in here to use my distance measuring tool measured at the center of my bolt. I zoom out and I select my second support and I click OK. So now we have an additional copy here for our second support. Holding down my control key, I'm going to highlight my additional support on the left-hand side because we would like to use the Move Copy tool once again. Using my distance measuring tool, I choose the center of my bolt and I move it to the additional right-hand side of my glass panel. And just like that, we have all 4 nodal supports defined for this particular model. So once we have completed this, I want to draw in the supporting structure as well. Now, for the sake of time, I've already done so in a saved model here. all I did was go ahead and draw the members that are holding up this canopy. So you can see we have some solid members framing into my bolt elements here. Our longer members are defined as HSS members with a 500 grade B material and so on. We actually can design these steel members per the AISC with the AISC module, along with glass design all in one program. So that's a huge benefit of RFEM, is just the multi-material design. So in addition to glass, if we wanted to design these members, we could. So I've even taken care of the loads here already. These are our typical loads that we saw before, snow load. The only thing that's different here is that under tools, generate loads from area loads on openings. I've utilized this for the applications here. What this tool does for us is we specify the magnitude of our load in kips per square foot along with the openings, and the program will actually apply it as a line load to the exterior of that opening. Now, the reason that I did this is because we have those rigid supports defined here, or those rigid surfaces. Those would suck up a lot of the load if we were to apply it just as an area load on top of it. So rather, we want to represent it with line loads at the exterior of this point support fitting. One other thing that I'd like to do within the program before we move on to our analysis is this canopy right now is completely flat. And in reality, we'd like it to have a slope of 5 degrees. And how we can define this, we're completely done with our modeling, our loading. We think, I really wish that I would have sloped this, but I have no idea how to do so without individually changing the elevation of each element in this elevation view. We can highlight our entire model, and under Edit, we have the option for chamfer. Chamfer allows us to slope all these elements at a particular angle, which will set this at 5 degrees. We're going to slope it about the global y-axis in the vertical direction z. Then we can choose an arbitrary point here where we'd like the canopy to begin sloping. So we choose the point closest to maybe our building where this canopy is extending out, and we click OK. So now you can see that every single element is now has that 5 degree slope. We didn't have to manually adjust anything. All of these contact solids, line elements, nodes are now sloped with that 5 degrees taken into consideration. So just a extremely useful feature if you didn't know it existed within the program. So finally, we're ready to jump into RF-GLAS, and realistically, not much is going to change here. What I do want to point out is that we're going to define every single surface here related to glass, of course, that we want to design for this detailed approach, meaning there aren't any additional steps we need to take. Everything can be done in this glass module. So we want to define all of our glass surfaces. So what I can do is I want to select my global panel here, but remember we have these small glass surfaces underneath our point fastener here. Well, they're a little bit difficult to select, so what I can do is jump to this Views tab, and I can view my surfaces by stiffness. And I have glass, I have null, I have my rigid, but I also have standard here. Well, these are just those standard concrete surfaces that I created in my template model that now I can select to be designed within the glass module. And what we also have lost here is our global surface. If I click OK, I also want to type in, we can just type that in manually to design surface number 1 as well. Everything else stays the same here. I'm going to copy all of these surfaces just by hitting Control-C. And under my Layers tab, I'm going to Control-V. I'm going to apply this laminated glass to every single one of these surfaces listed here. So I no longer have concrete within the model. We've now defined it with the laminated glass materials. Serviceability, I'm still only interested in designing this global glass support, or this glass panel. We're not really interested in designing those smaller surfaces underneath those connector discs for serviceability. And finally, we're ready to run our calculation. Now, because I've introduced so many more Efi Mesh elements into this model, it does take just a couple minutes to solve. So for the sake of time, I'm going to jump to an already saved model here with the solution. So what will be presented here is pretty much the same information that we saw for the simplified method, except for this time we can view all of the surface design for those smaller surfaces underneath those connector discs. So we're interested in the tension stresses underneath those connector discs as well as our larger panel here. So again, no additional hand calcs need to be run in this particular instance for tension stresses compared to the limiting design stresses. So now you can see this big red arrow is highlighted depending on where I'm at within my table here. We can jump to any one of these surfaces to see where exactly these controlling tension stresses are. And eventually we get a design ratio of 0.53. Max displacement, same concept here that we saw before. We're only designing our larger surface for deflection. So we're going to see approximately the same deflection that we saw with our simplified model of 0.17. Now again, all of this information can be viewed graphically, of course. So we're back in RFEM, but we're technically still within this add-on module RF-GLAS, and I can choose load combination 2 here, and maybe I'm interested in layer number 1, maybe the bottom of layer number 1. And now I can take a look at all of my different tension stresses. We can even zoom in here to those smaller stresses. And I've turned off my Fe Mesh, which you can do so under the display tab here. But even for these results, we can also highlight certain elements and create a user defined view. So now we're only looking at these two surfaces, so our panel adjusts accordingly to the upper and lower limits for only these smaller surfaces under these particular connector discs. So all in all, you can see a very different approach for simplified versus the more detailed analysis here. You should get relatively lower settings or lower design ratio when you're utilizing this detailed when you're comparing to the simplified. But hopefully it was some insight to the two different approaches within the program RFEM. So now we are ready to conclude our webinar today. So as always, I know these webinars are an extreme amount of information. You can always visit our website at dlubal.com for more information on RFEM as well as the add-on module RF-GLAS and all of our other add-on modules and possibilities as well. You also heard me mention things like our YouTube channel. We also have many other social media sites. YouTube, for example, has these recorded webinars that you can watch at your leisure. Newsletters, events, and conferences that we might be at, as well as knowledge-based articles are available on these sites and our website. Our email at our Philadelphia office is info@dlubal.com, and our phone number here is 267-702-2815. So if you have any questions about today's presentation or anything else related to our software, feel free to contact us here. So we will have many more upcoming webinars. I try and do them approximately once a month. You can always register at dlubal.com under support and learning and webinars. But as most of you know from today, I send out a couple reminder emails because they're not always placed on the website more than a week or so in advance of when I plan to present them. So keep an eye out for upcoming webinars. Many of you are wanting Pdh certificates for today, and that's great. We'll actually automatically send these out to all participants who were available for the full presentation today. So the states do require you to be available for the full webinar duration in order to claim that Pdh, and I will email that to the email that you use under the registration when you went ahead and applied online for this. Now, any additional attendees that maybe you watched with a colleague that you didn't register yourself, we can also provide you with Pdh. For that, can you please request that at info-us@dlubal.com. Again, if you didn't register individually for this webinar, please send an email to our office here at info-us@dlubal.com. And with that said, I want to thank everyone for attending today. And as always, we hope to see you at our next webinar. Thank you.